Good afternoon. Today we're going to look at a binomial expansion problem from IB higher level. This, I think, is a super interesting problem because it requires you to find specific terms in the expansion. And then once you've done the binomial expansion, there's an extra component where you're going to have to get creative and do some algebra to try and solve for a value for p. It's a very common type of problem, but it causes a lot of students problems because it really requires, in order to do it quickly, you have to have a pretty good understanding of how the binomial expansions work and how to set them up. So that's what we're going to focus on today. So to start by reading this through, it says, consider this expansion, 3x plus p over x to the power of 8. P, we're told, has to be greater than 0. I'm going to put a box around that because that for sure is going to be helpful later. The coefficient of the term x to the power of 4 is equal to the coefficient of the term x to the power of 6. Find the value of p. So already you can kind of tell this is setting up an equation that we're going to use later. Once we have the coefficients, probably in terms of p, we're going to be able to set them equal to each other and get a solution for p. But our first job is to figure out what those values for p are going to be. So if we start with a general term for this, we're always going to have 8 choose r. R, it doesn't matter which way we put this, but we're going to have 3 to the x to the power of r. And then we're going to have our second component, p over x to the power of 8 minus r. And what I'm doing here is I'm just trying to represent the fact that these two powers have to add up to 8. Because always in a binomial expansion, the power that your first component is raised to and the power that your second component is raised to, they're always going to add up to your overall power up here. It wouldn't matter if I put r or 8 minus r down here. But this is a good general term that we can use for any part of the binomial expansion. And we're going to use it here to try and figure out a lot of different solutions. Before I get into 4 and 6 specifically, I'm just going to try and simplify this using our power rules. So we have 8 choose, I'm on the eraser for some reason, we have 8 choose r, and then this 3x is raised to the power of r. So using our power rules, 3 to the power of r, x to the power of r. And then over here, we have something very similar, right? P to the power of 8 minus r, x to the power of 8 minus r. And to just simplify this, I want to combine it so that there's only one x term in my general definition here. So 8 choose r, 3r, p 8 minus r. I'm just getting all of the coefficient pieces together. And then separate to that, we're going to try and combine these. And the way this is going to work is, since this is a power on the bottom, we can think about this as x to the power of r over x 8 minus r. Another one of our power rules tells us that we can subtract the power on the base from the power on the top. So that's going to be r minus 8 minus or plus r, right? Because you're going to have r minus 8 minus r in brackets, and that's going to be 2r minus 8. So that's our power over x. Once we know, or we have an idea, that the power over x is going to be 2r minus 8, we can then use that to try and figure out what the values of r will be when we have an x to the power of 4, when we have an x to the power of 6. So if we start with x to the power of 4, that should happen when 2r minus 8 equals 4. 2r then is going to be equal to 12, and this gives me an r value of 6. So what's super helpful about this is once we've got a specific formulation for a basic algebra expression for the value of r, I don't have to think about 3x, I don't have to think about p over x, I don't have to think through combinations of guesses. I can just solve the algebra problem, get a value for r, and move on with the coefficient component. So we'll do the same for x to the power of 6. This is going to be 2r minus 8 equals to 6. So 2r then is going to be equal to 14, and r ought to be equal to 7. So we've got our two different values for r, one for when we have x to the 4, and one when we have x to the 6. And what's super helpful as well about this approach, once I know that that works, once I know my value for r, I already have a general definition for the coefficient of all the terms. So I can take r equals 6 And for x to the power of 4, go 8 choose 6, 3 to the power of 6, p to the power of 8 minus 6, which will be 2. And 8 choose 6 we can calculate. So that's 8 factorial, 6 factorial, 2 factorial. You can do this in a calculator, but it's good to practice because there are a lot of problems that require you to know this and know how to do it. You'll notice I'm leaving the 6 factorial in place, and I'm also stopping the expansion of 8 factorial at 6 factorial. So, 6 factorial represents not only 6, but it's also multiplied by 5, 4, 3, 2, 1. Those terms can just cancel very easily. And the 2 as well cancels here. So we've got 4 times 7. The coefficient is 28. So we have 28 times 3 to the power of 6 times p squared. And this will be the coefficient that goes in front of x to the power. This, then, is a process that I can repeat when I have x to the power of 6. So we go 8, choose 7, 3 to the power of 7, p to the power of 1. Because we're doing, p is 8 minus r, so 8 minus 7 would be 1. 8 choose 7, hopefully, is just 8. So we have 8, 3 to the power of 7 times p. And this is the coefficient that goes in front of x to the 6th. What's super useful about this, and there's a reason I'm not simplifying the 3 or the p, right? I'm not going out and figuring out what 3 to the 6 is or 3 to the 7, because I have an idea that these are going to cancel. When we set the two terms equal to each other, I don't really want this as a big expanded number. It's going to be pretty easy for me to just cancel it from both sides of the equation. So we were told the coefficient of the term x to the power of 4 is equal to the coefficient of the term x to the power of 6. Well, now I have a coefficient of x to the power of 4, and I have a coefficient of x to the power of 6. There's a 2 there, I don't want to forget that. So 28 times 3 to the power of 6 times p squared should be equivalent to 8 times 3 to the power of 7 times p. And I can sort of rewrite these as fractions, try and cancel things from both sides. So 3 to the power of 6 is going to go away. This then becomes a power of 1. 8 and 28 have a common factor. So I'm going to cancel, let's see, 28 is 7 times 4, so we can replace that with a 7, and that with just a 2. So factoring 4 out of both. And then p, I can replace with a 1. So we have 7p equals 2 times 3. And then p is going to be 6 over 7, like that. If you're going to be big gung-ho and cancel everything like that, you do want to go through and double check that you've done all of that correctly. If not, go through the work and sort of do it a bit more slowly. I'm just going to double check. We cancelled a 4 from 8 and 28, so we were left with a 7 and a 2. We cancelled 6 3s, so all of those went away. All but 1 went away here. We cancelled a p and the square, so we're left with 1p on this side. So we have 7 times p, 2 times 3, and that's 6 over 7. That would be our value